Welcome everyone. In this lesson we're going to be looking at Lagrange multipliers, and this is going to be one of our optimization techniques. So to get started, we're going to come back actually and think about the proof of this, or kind of an idea for the sketch of the proof of this technique. So we'll come back to this. But let's look at an actual statement for what the method of Lagrange multipliers is and what it's going to help us do. So we're going to be interested in finding the maximum or minimum values of a 2 or 3 variable function usually. So as it's written here, f of x, y, z. So we want to maximize or minimize this function subject to a constraint. So Lagrange multipliers is going to help us maximize or minimize, find the maximum or minimum for a function subject to a constraint. So there's going to be kind of two equations floating around here that we're going to work with. And the way we're going to do this is, well, call it step 1 here, but this is going to take some work. And we're going to find all of the values for x, y, z, and lambda such that this equation is true and this equation is true. So the gradient of function f is equal to some constant lambda times the gradient of function g. So we're doing the gradient of f, the gradient of g, and we're basically setting these two gradients equal to each other up to a constant. So it's that lambda is a constant. And, you know, we're going to call this the Lagrange multiplier here. So this lambda here is the Lagrange multiplier. And it's just a constant. All right, so when we go to solve an optimization problem like this with a constraint, we're going to first set up our Lagrange equations. So we're going to set the two gradients equal to each other and then throw a constant in front of the gradient for g. And then we're also going to have our constraint equation to work with. And then what we're going to do is we're going to solve these equations for x, y, z, and maybe lambda. And then we'll plug into our original function f and see which one gives us the largest and which one gives us the smallest. Now when we do this, let's just kind of write out what these Lagrange equations are going to look like. So we're going to have 3, maybe 4, depending on how many variables we're working with, Lagrange equations. And so let's write out, what is the gradient of function f? Well, it's f partial x, f partial y, f partial z. And what's the gradient of function g? Well, it's g partial x, g partial y, g partial z. So what we're doing, the way two vectors are equal to each other is if each of the components are equal to each other. So our Lagrange equations here, we're going to have our x partial equation that says f partial x is equal to lambda times g partial x. And we're getting that from the first component of our gradient equation there. Then we're going to have f partial y is equal to lambda times g partial y. So we have our y component from the gradients, and we set those equal. And then we also have our z component. So the f partial z is equal to, again, that same Lagrange multiplier lambda times g partial z. And this is for a 3 variable setup. And then we also have our constraint equation. So we're going to have these partial derivative equations and then also our constraint equation. So we're going to use that to work with as well. So this is written for the 3 variable case where we have a function in terms of x, y, and z. If it's a 2 variable case, well then we're just going to have the first 2 of these equations and also a constraint. So let's try an example here, going through the technique of Lagrange multipliers, and then we're going to back up and actually see what's going on kind of behind the scenes with this. So let's look at, we're actually going to jump ahead. We're going to look at example 2. We're going to do example 1, don't worry. But for right now, we're going to look at example 2. So we want to find the extreme values for the function f of xy. So we're in the 2 variable case. And our function here is x squared plus 2y squared. And we want to find the extreme values subject to this constraint, that they have to sit on the circle x squared plus y squared equal to 1. All right. So graphically what's going on is we're looking at f of xy is a surface, and that's what we're seeing right here is our surface. And then we're looking at our constraint, which is x squared plus y squared equal to 1, or equal, what is it? Yeah, x squared plus y squared equal to 1. So that is right down here. And what we're doing is, by looking at this constrained optimization, we're looking at all the points that sit on our surface that are above this circle. So we're kind of looking at the intersection here between the cylinder x squared plus y squared equal to 1 with our actual surface f of xy. So essentially, we're looking at all these points on our surface that sit above this circle. And what we want to do is we want to find where on that circle, where is the high point? Or maybe back here. And where on that circle, where are the low points? So that's what we're trying to locate is just on this curve, where are the high points and the low points? Not on the entire surface, just on the surface, but constrained to this curve. So that's how the interaction's going on. We're looking on the surface, but we're only looking at a kind of a portion of the surface where it's constrained to a curve. All right, so let's set up our Lagrange equations. That's really the first thing we want to do. So again, let's write out the general formula here just to kind of get going. So we're dealing with 2 variables, so that means we're going to have our x partial. So f partial x, we'll set that equal to lambda g partial x. And then we'll do the same thing for y. So we'll have f partial y set equal to lambda times g partial y. And then we'll have our constraint. All right, so what is function, well, we're told what function f of x is, or f of xy. What's g? Well, g is just this variable part of the constraint equation. So here, g of xy is x squared plus y squared. All right, so let's actually get things going. So let's do our x partial with of our function little f. So when we do that, derivative with respect to x here is going to be 2x. And then we're going to set that equal to lambda. And then we do our x partial for our g function. So in this case, also 2x. All right. Now we go to our y, do the y partial for our function f, we get 4y. And then we're going to set that equal to lambda, and then we're going to do the y partial for our g function. So in this case, 2y. And then we're going to need our third equation, which is just our original constraint. So let's just write that down. X squared plus y squared equal to 1. All right, so now we want to try to solve these 3 equations simultaneously. So there's 3 unknowns, 3 equations. So there's x's we don't know, y's we don't know, and then lambda. Now lambda we might not actually have to solve for. Maybe we do. We'll see. All right, so let's start with the first equation. And when we look at this, it might be helpful to kind of move all the terms to one side and see if you can factor. And in this case, it does. So let's move the lambda 2x over to the other side and try to factor. And when we do that, we get 2x times, well, actually, let's write out what we get. So we get 2x minus 2x times lambda, set equal to 0. And then we can kind of factor that a little bit. So we can factor a 2x out, and then we have 1 minus lambda. And this is all equal to 0. And then essentially each of these factors then gives us a possible solution. So the 2x factor here gives us x equal to 0 if we set that equal to 0 and keep solving. And then if we look at the 1 minus lambda factor, set that equal to 0 and keep solving, we get lambda equal to 1. Okay, so that's what we get from our first equation. Let's see what we get from our second equation. And let's try something similar over here. So let's try moving all the terms over to one side. So we'll write this as 4y minus 2y times lambda equal to 0 once we move it over. And then we can factor. So we can factor a 2y out. And then we have 2 minus lambda equal to 0. And in this case, let's keep solving. And we can set each of these factors equal to 0. And when we set the first factor, we get y equal to 0. And when we set the second factor, we get lambda equal to 2. All right. So what we're trying to do is we're essentially trying to almost find the critical points. They're not critical points, but that's kind of what we're doing, is we're trying to find on this specific curve, where are we hitting the high points and low points. So we're trying to look for the x and y coordinates. All right, so let's start with our x equal to 0. So let's take each of these results that we got and see if we can extract out what the coordinates are. So let's start with x equals 0. So if x is equal to 0, we can go to our constraint equation. That's the one equation we haven't used yet. We can go to our constraint equation, plug x equals 0 in, and see what we get. So we go to our constraint, plug it in, and we get 0 squared plus y squared is equal to 1. And if we keep solving that, we get y squared is equal to 1, which tells us y must be equal to plus or minus 1. All right, so conceivably, we have 2 points now given by those x and y coordinates. We just kind of pair them up. All right, so that's the x equals 0. What about lambda equals 1? So if lambda is equal to 1, let's see what we get. And for this one, we're going to go to our second equation, and we're going to plug, now there's no lambda over here for our constraint, so we got to go to the other equation. So we got lambda equals 1 from the first one. Let's go to the second equation now and plugged lambda equals 1 in. So when we plug that in, and I can go to any of these, I can go to here, I can go to here. Let's actually go to that last one. So when I plug lambda in to our second equation, I end up with 2y times 2 minus 1 equal to 0, which if we simplify gives us the equation 2y is equal to 0, which actually gives us y equal to 0. So we actually already found that information. So this lambda equals 1 actually doesn't give us any new additional information. We already came up with that y equals 0. So we'll save that for later. So we already found this. All right. Well, now let's actually deal with that. So let's take our y equals 0 and plug it into our constraint. So let's go to our constraint. Now this time I'm plugging 0 in for y, so I'm going to leave x as is. So I have x squared, 0 in for y. And so when I do that, I end up with the equation x squared is equal to 1, and then we get the solution x is equal to positive 1 or x is equal to negative 1. Again, when we do the square root, plus or minus. All right, so right now it looks like we have 2 points with an x-coordinate of 0 and 2 points with a y-coordinate of 0. We also got this lambda equals 2, so let's see what we get from that one. And so again, there's no lambda in our constraint equation. So since we got lambda equals 2 from that second one, let's actually take that result and plug it in back over here. And if we do that, let's see. So we're going to plug it into our first equation. And when we do that, and again, we could plug it into any of these. So I could go here, here, or here. This one's probably a little bit easier since we've already done a lot of the factoring. So I get 2x times 1 minus 2 set equal to 0. And then if we simplify that, we get negative 2x is equal to 0, which gives us x equal to 0. And we already worked with that. So that sometimes happens. Perfectly fine. Is that sometimes you get a little bit of redundant information. All right, so if we're looking at this, the main things we found came from the x equals 0, and that gave us 2 points. And then also y equals 0, and that gave us 2 points. So now we just want to actually consider what the min and max values are. So we want to look at the points 0, 0, 0, 1, and 0, negative 1. And then also 1, 0, and negative 1, 0. So we have 4 points here that we want to consider. And so we want to actually plug each of these coordinates into the original function little f. So if we go up to our function little f, where was it? It's right here, x squared plus 2y squared. So let's see what we get when we plug in f of 0, 1. So it's going to be 0 squared plus 2y squared. So we end up with 2. And then if we do the same thing for the other 3 points, when we plug in the 0, negative 1, we're going to get 2 again. And then when I do f of 1, 0, we get 1. And then f of negative 1, 0, we also get 1. And so what we're seeing is the maximum occurs at 2 points, and the min occurs at 2 points. So the max value is equal to 2, and it occurs at the point 0, 1 and the point 0, negative 1. And then our min value, we see the lowest value here is 1. And this occurs at 1, 0 and negative 1, 0. So what we've seen is by solving this equation, we've actually located these points that we can kind of see where they sit on the graph. So we found that when the x-coordinate was, so at the point 1, 0, that was a minimum. If we look at the point on the curve, that has the lowest height for this section of this curve. And then same thing at the point negative 1, comma 0, there is also a low point over there. So we had a min and then a min over here. And then for the points 1 comma 0 and then 1 not 1 comma 0 backwards 0 1 and 0 negative 1, these were where, if we look at the points on the graph, that's where we actually had a max, a high point on our curve. And the height for that high point was 2, and the height for the low point was 1. All right, so this is the technique of Lagrange multipliers. And so we're going to, and the second part of this was to actually evaluate to see which one's giving us the high and the low. So what we're going to look at in class is we're going to, well, first of all, do a few more examples. And then we'll also go up and we'll kind of give a little semi-proof, more of just reasoning for why this Lagrange technique actually works to help us find the max or the min. So we'll see you then. Bye-bye.